Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. In this video, we will learn about applications of sequential logic outside of recipes and phases. The first topic we will visit is shared resources. We talked about how in the SAD8 hierarchy, we would focus on unit modules, equipment modules, and control modules. Above that level, the questions of control are mostly problems of scheduling, logistics, and the optimization of both, which is beyond the scope of this course. But a problem that is typically addressed within process control is shared resources, a resource that is outside of a unit because it is shared by more than one unit. Typical shared resources include storage tanks and heating or cooling utilities. Let's look at a batch process plant that has raw materials stored in a tank farm where the charging of raw materials A and B are through a common piping and metering system. The common resource is mutually exclusive. That is, only one of several units that require A or B can use the charging system at one time. The problem is clearly what to do if more than one unit requires shared resource raw AB at the same time. The solution is an ownership system. When a unit wishes to charge A or B, it sends a request to the raw AB resource to temporarily own that resource. The unit has to wait until it gets a reply that it now owns the shared resource, and then the charge can happen. Raw AB has to maintain a piece of software that receives requests, puts them in a queue, and grants ownership to one unit at a time. When a unit finishes a charge, it returns ownership of the shared resource, and raw AB moves on to the next unit in its request queue. The next common shared resource problem is a resource that can have multiple users, but is limited, and therefore needs to be rationed. This can happen with a hot oil system, for instance, which has a limited heating capacity serving several batch systems with varying heat demands. If the combined units ask for more heat than the heater can deliver, the ability for all of those units to control temperature may be compromised as the hot oil temperature falls. The solution to a limited resource problem is a rationing system. When a unit needs heat, it sends a request to the resource manager, which will be a piece of code. The resource manager then has to decide how to allocate the available heat, generally through a priority list, and replies to each unit with their allocation. Here, with the three units together requesting more than the capacity of the heater, the lowest priority unit is allocated less than its request. Each unit needs to be able to control their heat flow so that they don't take more than is allocated. Systems like this can be found with limited capacity hot oil, steam, cooling water, absorber, or scrubber systems. The next area where sequential logic is very important is for continuous processes. But you may be saying, continuous processes don't have sequences, they maintain one state in time. Which is true, but only when they're already operating. Every piece of process equipment starts and ends dry and at room temperature and atmospheric pressure. Startup, shutdown, heat up, and cool down procedures all require sequences if automated. And as these transitions are by their nature the occasions with the greatest risks for safety and the environment, in a modern plant they will be automated. For continuous processes, we'll generally call the desired operating state or mode production, and we'll generally have a state called shutdown, where we're safe and ready for maintenance. We need to transition between shutdown and production through intermediate states that will depend on the unit in question. Often there will be an idle or ready state where process flows have yet to start, but utilities are switched on to bring temperatures and pressures to target points ready for the first process flows. The other most common states are heat up and cool down, as we often need to change temperatures gradually to accumulate heat or to avoid damage to the equipment or process fluid quality. Here we have a vacuum continuous distillation column, similar to those we worked on in the Chapter 1 Degrees of Freedom exercises. It fractionates a feed into a distillate and bottoms product using a total condenser and a thermosiphon reboiler. In production state, feed is taken from T1, preheated and distilled in our vacuum column. An in-spec product is sent to T2, the distillate product tank, and T3, the bottoms product tank. In shutdown state, there is no feed, no liquid inventory, no heat to the exchangers, and pressure is broken back to atmospheric with nitrogen. To get from shutdown to production, we'll first use an idle or ready step. Pressure will be reduced to the desired operating level using the P3 vac pump. A little steam fed through E2 reboiler and E3 preheater to heat them up, and water flow started through E1 condenser. Heat up state starts feed to the column. The preheater and reboiler will raise temperatures, but many continuous columns take hours to heat up all the metal, start producing vapor, get a good reflux flow going to allow fractionation, and finally reach the production temperature and pressure parameters that indicate acceptable quality product. During heat up, we don't want the off-spec distillate and bottoms to go to product tanks, so this column has the option to recycle the distillate and bottoms to the feed tank T1. Heat up can have several changes of equipment state and transitions as feed flows are increased and reflux flow established, so it's good to write it as a sequential function chart like you would a phase. If we look at a diagram of our production states, the arrows indicate the allowable paths. We can go from any state to shutdown, as that is our emergency abort state as well as our safe state. But from shutdown, we can only move to idle. From idle, we can move to heat up, but not to production. We can only reach production by satisfying the quality conditions in the heat up sequence. Each of these states represents a list of commands to control modules, valves, pumps, and controllers, or in some cases like heat up, a full sequence of commands to devices. See the text for sequential function charts describing in detail each of the 4 production states for this column. 2 notes. 1, a lot of processes might also have a cool down state, which is essentially heat up in reverse, using process flows to cool equipment gently before stopping flows in an idle state. Second, a column like this will have many cascaded controllers, constraint controllers, and many digital interlocks together with these operating state sequences. Having them all work together smoothly is a challenge that requires planning and careful design for a complex unit like a distillation column. Today we learned about using shared resources outside of batch units and using sequences to facilitate safe and effective startup and shutdown of continuous units. Look for a full text, exercises, and more videos at chemicalengineeringpractice.org. I'm Tom Meadowcroft. I hope to see you again soon.